very good evening to all the attendees and to Dr. R.S. Swathi, who is there at IISER Thiruvananthapuram. And she is going to talk to us today on the topic carbon membranes for separating mixture, theorist perspective. And this particular special public webinar is part of the school outreach program, which is jointly organized by the National Academy of Sciences India Delhi chapter and Deen Dayal Upadhyaya College, University of Delhi, under the aegis of the DBT Star College program. At the outset, I would like to thank Professor Anurag Sharma, who's the chairman of the NASI Delhi chapter, as well as Professor Ajoy Khatak, who's the president of the National Academy of Sciences India, and to all the team members of this NASI DDUC Science Promotion Activities Initiative. So before inviting Dr. Swathi to deliver her talk, let me briefly introduce her to all the students and the teachers who are attending this program. So she obtained an integrated BSc degree from Regional Institute of Education, Mysore, and an MSc degree in chemistry from IIT Guwahati. Subsequently, she pursued PhD in theoretical chemistry from Indian Institute of Science, Bangalore, working under the supervision of Professor K.N. Sebastian. Since 2010, she has been working as a faculty member at the School of Chemistry at IISER, Thiruvananthapuram, and is currently an associate professor there. Her multi-scale modeling and computational group employs analytical and computational approaches for modeling interesting phenomena involving carbon-based and metal-based nanostructure. She is a recipient of the Young Scientist Award from INSA, National Academy of Science, Kerala State Council for Science and Technology and Environment, and Distinguished Lectureship Award from the Chemical Society of Japan. She was also a Young Associate of the Indian Academy of Science, Bangalore, and a recipient of the A.V. Ramarao Foundation Prize in Chemistry, awarded by the JNCSAR Bangalore for the year 2020. With these words, I request Dr. Swathi to kindly share her screen. And we also have on our panel, Dr. Vinod Kumar. He's a senior faculty in Deen Dayal Upadhyaya College and Department of Chemistry. Yeah. Over to you. Yeah.
Good evening. Thank you, everyone. I hope you can see the screen.
Yeah, maybe if you can put it in the slideshow. Yeah.
Is this all right?
Yes, perfect.
Yes. So good evening, everyone. Let me first begin by thanking Professor Saxena for this very nice initiative of engaging the students with exciting lectures from all domains of science and mathematics. I am really pleased to be delivering this talk. It's always a pleasure to talk to the students. So in the next 30 minutes or so, what I'm going to do is I'm going to take you through a perspective of a theoretical chemist, or you could say a theoretical physicist, because the boundaries are very, very blurred. So the problem that I have chosen here to talk to you today is carbon membranes for separating mixtures. And I know that most of the audience are school students, and therefore I begin with the textbook example of separating mixtures using very, very conventional approaches that one learns in chemistry. These approaches are, for example, distillation. One specific form of distillation is fractional distillation that is extremely popular. We are also familiar with chromatography, for instance, and evaporation. Of course, salt evaporation is a very, very common problem that we study in chemistry. Okay, and all of these in some or the other form deal with separating mixtures, right? The property that is of interest in each case is of course different. Likewise, you could think of centrifugation, which basically enables separation of species based on their densities. You could also think of extraction process. Likewise, you could think of magnetic separation. All right, magnetic separation, of course, depends on the magnetic properties. For instance, if you have an iron fillings and sulfur mixed, and if you use a magnet, you should be able to separate out the iron fillings from sulfur. That's the idea. And then, of course, you can have filtration, the conventional filtration technique that all of us are familiar with. All right, so these are some textbook examples that we learn in chemistry. And why are they important? Because most often on an industrial scale, when people work with chemicals or in a routine laboratory setup in an academic setting, we have to deal with this problem of separating various chemical species. And therefore, depending on the system at hand, meaning the species that you want to separate, you devise methodologies that you can resort to. For example, in some cases, boiling point may be a property that is of interest. In some cases, density may be a property that's of interest. In some cases, it may sheerly be the size of the particles, as you can see in filtration. Okay, so nonetheless, the point is that all of these separation techniques are extremely useful for chemists. Now, the focus of today's discussion is on a very specific separation technique, which is called filtration. And filtration using macroscopic membranes is something that all of us are familiar with. For instance, if we make a cup of tea, we know that the tea dust has to be separated from the liquid, right? The tea liquid that you have in the house. So all of us, in some sense or the other, have basically employed this technique for separating. Now, how is it different from what I'm going to be talking to you about today? It is that in, for example, the techniques that we use in everyday life, these membranes that we have are actually what are known as macroscopic membranes. All right. But the topic of discussion today is basically achieving separation using what are known as atomic thin membranes. Okay. Basically, what I'm talking to you about are very, very thin membranes, and they are precisely 1 atom thick, meaning that the thickness is basically the size of a single atom. Okay. So macroscopic membranes are something that we are familiar with in our everyday lives, while microscopic membranes are what I am considering for discussion today. Okay. And size sieving mechanism is extremely popular. As you can see in the video out here, if you have particles of different sizes, depending on a choice of a membrane, you can basically separate out these into their individual components. And this is very easy to imagine for us. Okay. So the special topic of discussion today is basically on carbon membranes. Okay. Graphene is extremely popular in current times and is heavily researched over the last 15 years or so, because in 2004, people have been able to structurally characterize a single layer of graphite. Graphite, as all of us know, is basically layered material, okay, which means several layers of carbon are stacked together. If you pick up one such layer, that is what we refer to as graphene. Now, the discovery of graphene had to wait until 2004 because the experimental structural characterization tools for characterizing 1 atom thick membranes were simply not available. Okay, meaning scientists wanted to see single atom membranes, and if one were to do that, one needs to resort to high resolution spectroscopic and microscopic techniques. And that is why it took so long for us to basically reach the discovery of graphene. Nonetheless, over the last 15 years, several applications of graphenes were explored. And one such application is what I'm talking to you about, which is separating chemical mixtures using graphene. Now, if you think about the structure of graphene for a moment, you will realize that it is almost impossible to separate chemical species using such a 1 atom thick carbon membrane. Okay, why do I say that? Think of all these examples that are shown out here, various ions, molecules, which are extremely tiny. Okay, if one were to basically think of separating these species by passing them through the graphene membrane, the hexagonal pore of the membrane should be in principle able to allow the passage of these species through them. Okay, and if you roughly look at the sizes, you realize immediately that none of these species would in principle be able to permeate through this tiny hexagonal pore except for the proton, which is the smallest. Okay, so graphene is practically impermeable to most chemical species that one can think of. And then the question comes, okay, then what use is it for various applications? Because obviously I am basically interested in looking at reasonably sized chemical species separating using graphene, and that is seemingly impossible with such an approach. Okay, this made scientists to think of ways in which they can exploit graphene for these applications. Okay, graphene has very, very beautiful properties in terms of hardness, electronic properties, mechanical strength and all that. But let us not talk about all those details today. But suffices to say that scientists are extremely intrigued by the possibility of using graphene for various applications. Now, if one were to use them for membrane-based applications, there is no way but to actually drill pores through the carbon membrane so that you have larger pores in which you can pass chemical species and you should be able to separate the species. That's the idea. Now, how do you drill pores through a carbon membrane? Typically, what experimentalists do is they use high energy electrons or high energy atoms and ions to basically knock out certain carbon atoms in the carbon membrane that you see out there. This process basically leads to formation of these nanopores. Okay, and these architectures are what we refer to as graphene nanomeshes. Okay, nanomeshes, because these are meshy architectures with nanometer sized domains. All right, so it turns out that it is indeed possible to drill pores and to employ them for various separation applications. One such specific class of graphene nanomeshes is what I'm showing here. So as you can see on the pores of these nanomeshes, you can see heteroatoms, the red colored balls, as you can see, those are nothing but oxygen atoms. Okay, so in 2014, scientists have actually devised ways in which they can bring oxygen atoms in the pore architectures to the graphene membrane. And not only that, they can actually control the pore size by doing this. And that's remarkable because if you can control the pore size, that means you should be able to, in principle, design ideal pores that will allow selective separation of various species. For example, let's say I have a gaseous mixture of carbon monoxide and hydrogen. I would like to separate hydrogen from carbon monoxide. Then in principle, it should be possible for me to design a very tiny carbon membrane that will allow the separation of carbon monoxide from hydrogen. Okay, that is the effort that I'm talking about now as I go along. Okay, so now it turns out that it is possible to actually drill such pores and characterize them. And one such beautiful experimental demonstration is what I show here. Please ignore the frame that you see on the outer region of these images, but on the background, what you see are real experimental images of these graphene nanomeshes. Okay, these are very, very fancy experiments that have been performed using scanning transmission electron microscope, which is high resolution one. Okay, but nonetheless, you might not be perhaps familiar with the technique, but suffices at this stage to tell you that it is possible to actually locate individual atoms using sophisticated spectroscopic and microscopic techniques today. Okay, and you can see a clear example of these four images as you go from the left-hand side to the right-hand side. Individual atoms are basically seen. Of course, what is superposed on the top are a set of models from various modeling approaches. I shall come towards modeling in a few minutes. All right. So today it is possible to characterize such membranes. Now, why do we worry about looking at separating species through carbon membranes? It is not as simple as, you know, when you have two different particles of two different sizes, you design an appropriate pore to separate the smaller one from the larger one. No, so the story is far from that. It is today possible to actually design smart membranes that can enable separation of very, very interesting species. Okay, for example, you can think of isomers of hexane. Each of them can be selectively separated by carefully designing pore architectures of various smart membranes. And it is here that the role of modeling and simulations comes in. Because typically what happens is one has to try out several combinations before coming out with a successful one. And this is often very difficult in experiments. And therefore, what we do is that we compute properties, we model these phenomena using interesting modeling formalisms. I shall come to them as we go along. So the point is, you can try out several combinations for carbon membrane architectures using computer models and come up with an optimal membrane that can do the job for you. And eventually it would be nice to try out that optimal membrane in an experimental setting and to see if indeed works. And this is where the power of theory or modeling comes in. All right. So now, supposing I ask a question that if a species is permeating through a membrane, okay, how do I model this problem? one has to basically think of what is the potential energy that the particle sees as it goes along through the pore. Okay, and this typically turns out to be having two kinds of potential profiles. One is a flat potential, as you see here, and the other is a typical double well potential. Okay, let me explain to you physically what it means. So you have a membrane. Typically under equilibrium conditions, the particle can bind somewhere here. It can also bind somewhere here. And these two are equivalent, right? As far as you see it physically, binding here and binding here should be equivalent. And therefore, those two are the most favorable minimum energy configurations on the double well that you find here. But then as the particle goes from one end to the other, it kind of goes into the pore, but then that's not very comfortable for the particle, provided the size is appropriate to that. Then what happens? The energy of the system rises, which is what you see as an energy barrier here. So you basically have two minima that are separated by an energy barrier. So you can see the permeation through the membrane is basically modeled as a potential in a double well, right? And this typically one generates using quantum mechanics. Now, why do I say quantum mechanics here? We are talking about, remember, one atom thick carbon membranes. We are talking about pores that are few angstroms in size, which means that if you were to infer any meaningful properties, you need to resort to quantum mechanics. Classical mechanics would not suffice. Supposing if I were to ask a question that I take a bus here today at 5 p.m. and I ask the question as to if I went in a particular direction, where would the bus be after 15 minutes? I know that I can use Newtonian equations of motion to analyze this problem. But if you were to start with a particle that is on one side of a membrane, and if you were to ask about the permeation through the membrane and to the other side, you cannot use Newtonian mechanics to solve such mechanics problems. Okay, simply because we are dealing with subatomic or atomic particles. In other words, the world of atoms and molecules is typically governed by quantum mechanics, and Newtonian mechanics fails under such circumstances. Okay, which is the reason why I say that you need to resort to highly accurate quantum mechanical calculations to generate these potential energy surfaces. Okay, now to the students, if you are really interested in modeling such problems, theoretical chemistry or theoretical physics is the way to go. All right, if this is what excites you, please pursue theory, and you will have answers to many of these questions as you go along in education. All right, so now let me get into the details a bit more. So basically what I told you is that the permeation problem can be modeled as a double well, and this typically could be seen as a chemical reaction. Okay, so the transmission across the barrier could be treated as a chemical reaction. Okay, so if we think of chemical reaction, we know that there must be reactants, there must be products, right? And there must be transition states as one evolves from reactants to products. In this particular case, the reactant is a configuration where the particle is on one side, while the product is another configuration where it is on the other side. And of course, the transition state is one where it remains in plane with the pore, nanopore I'm talking about. Okay. So now let me start with the simplest example that you could think of, which is known as the size sieving mechanism. Basically what it means is that two particles are separated based on their sizes. Okay, so a simple example that you can think of is helium, neon, argon, and krypton, noble gases that you're familiar with. And as you go from helium to krypton, you know that the size increases. And if you choose a special nanopore of this kind, you can use quantum mechanics to calculate the barriers. And that will tell you as to what is the energy cost that is there to allow the passage of a particle from one side to the other. Okay, it's not very difficult to see that it should be easy for helium to go through the pore, but it should be very, very difficult for krypton to go through the pore because krypton is hefty. Okay, and therefore, even without doing a calculation, we should be able to easily comprehend the fact that the energy barrier for krypton should be very, very large in comparison with that of helium. Indeed, that is how the calculations turn out to be. So you can see that the barrier for helium is in green and the barrier for krypton is in pink, and it increases as you go from helium to krypton. Okay, these are from accurate quantum chemical calculations. All right. Now, so my question is, if I have a mixture of, let's say, helium and neon, how do I quantify the abilities for the membrane to separate helium from neon? Okay, one such quantification is what is known as a selectivity factor. Okay, what is a selectivity? It is basically the ratio of the diffusion constants or the rate constants for the permeation of helium to that of neon. Okay, and rate constants, of course, there are more rigorous ways of evaluating. We resort to what is known as transition state theory. Again, you're probably not familiar with this, but you would learn them as you go along, let's say, to BSc and MSc. All right, suffices to say at this moment that from the computed energy barriers, you can actually calculate diffusion rates. And from the diffusion rates, you can estimate selectivities. And what does the selectivity tell you physically speaking? I have a bunch of helium neon gas atoms in a large container. What is the selectivity with which I can separate helium from neon? Right? This question is basically quantified by the selectivity factor. And as you can see, we can calculate the diffusion rates for various temperatures, selectivities for various temperatures. And diffusion rates, of course, increase with an increase in temperature, while the selectivities drop down heavily with an increase in temperature. Okay, that's not very good news, because if the selectivities drop with an increase in temperature, then industrially, if you would like to employ such a process, it's extremely difficult. Okay, you need to really go down to very low temperatures to be able to achieve significant selectivities from such systems. So therefore, modeling again can contribute by actually designing membranes that are appropriate and that can do this job much better. All right. So these are some details for the same size sieving mechanism. I will not dwell upon it due to restrictions in time, but I shall give you an example to say that all this is not just pen and paper or a computer business. This is actually much more to do with even technological relevance of such phenomena. All of us are familiar with reverse osmosis membranes that most of us use in our homes for purifying water, right? So now purification of water is governed by membrane-based technologies. Recent experimental or modeling findings have indeed shown that graphene membranes can be excellent for purifying water, which means that they have a good ability to separate the ions from water, pure water molecules. And that means that they have a great potential to go on to become technologies. In fact, this particular graphene 4 membrane has been shown to yield an unprecedented water permeability, orders of magnitude higher than that of what we have today commercially in reverse osmosis membranes. So you see that modeling doesn't really have only theoretical relevance. It has a great technological relevance. If you can pursue good computer models, good pen and paper model formulations, then you can actually contribute to technologies. It doesn't have just a theoretical value, right? So this is an example which tells you that modeling can indeed contribute to technological innovations. Now, the second example that I shall talk to you about today is to think of a membrane that is a smart membrane. Okay, why do I say it's a smart membrane? You think of this example, there is a red ball and a blue ball. What this smart membrane does is it allows selectively the permeation of the red ball while blocking the blue ball. Okay, how does it do it? Let's go on to the details. There are 3 pores that one considers. Okay, the pore architectures are what are shown here. The pore sizes are also what are shown here. Typically, the example that I'm talking to you about today is separability of CO2 and NO2. Okay, and the sizes of CO2 and NO2 are given below. If you look at this pore, which is H pore 13, which is very special because the smaller one, of course, would not allow both molecules to pass through. The larger one would allow both molecules to pass through. While this particular special pore, pore 13, it allows selectively the larger guy to permeate while the smaller guy is held back. How does it do that? It does it by way of what is known as chemical affinity sieving. So what it means is that it exploits the fact that there are favorable electrostatic interactions when you have CO2 versus N2. You can look at the charges on the partial charges on the nitrogen atoms here and the carbon and oxygen atoms here. Because the CO2 molecule has significant electrostatic contribution, the molecule actually gets stuck in the pore while allowing the permeation of N2. Okay, and this gets stuck in the pore because on the pore what you have are hydrogen atoms which have positive charges, and they kind of get attracted to the negative charge coming from the oxygen atoms. Okay, so this is referred to as chemical affinity sieving because it's based on the chemical affinities of the species that you are wanting to separate, that you are able to achieve this sieving process. All right. So next, I shall go on to tell you the most interesting example for today, which is basically quantum sieving, which means that you can have a separability of even helium isotopes using smart membranes. Okay, why do I say helium isotopes? You see, when you think of helium isotopes, helium-3 and helium-4, it's extremely difficult to separate them because their most properties are very similar. And therefore, if one were to separate them, the only way seems to be to exploit the difference in the subtle difference in the masses of these particles. And that's exactly what comes into play here by way of tunneling. Okay, tunneling is a very, very popular phenomena in quantum mechanics, and there is no classical analog to it, which means that there is no real life example that we can use to relate to tunneling. Let me give you an example. Let's say you think of a particle that comes in, and if the barrier that the particle sees is large, then the particle would never go through the barrier, it returns back. Okay, the particle simply doesn't have enough energy to cross the barrier. Classically, the transmission probability is 0. Okay, the particle will never be able to cross the barrier. But quantum mechanically, what happens is that even if the energy of the particle is small, there is a non-zero probability for the particle to actually tunnel through the barrier. And this phenomena has its own beautiful manifestations. And in this particular case, you can see that this phenomena indeed allows us to separate helium-3 from helium-4. Okay. So as you can see, the dashed line here is basically what tells us as the energy barrier. Okay, now you can see that the orange and green curves on the lower tail indicate that the energy of the particle is below the barrier, but still the particle has non-zero transmission probability. Okay, which means that this is purely a quantum mechanical effect. And if you were to use a simple example to understand this, this is an example that you could think of. So this is a model problem that one often encounters in quantum mechanics. It's called particle in a box with one finite wall. Okay, so what it simply means is this: if you think of a particle that is confined to move in such a potential, even if the energy of the particle is below the barrier, or if you think of the bound states, okay, all these red lines correspond to energies that are below the potential that it sees on this extreme end, right? Okay, despite this, the particle is able to go through the barrier and go to the other side of the barrier. So on the right hand side here, what you see are what are known as the wave functions of the system. A wave function is basically a property that has all the information about a quantum mechanical system in it. You can extract all parameters that are of interest to you by employing the wave function. You can calculate positions, you can calculate momentum, you can calculate average angular momenta and things like that. Many, many properties that could be of your interest by employing the wave function. In other words, wave function is a central property in quantum mechanics, and you arrive at it by solving what is known as the Schrodinger equation. I mean, I'm sure all of you are familiar with classical Newtonian mechanics, right? So the Newton's equation F is equal to ma allows you to solve for the equations of motion and allows you to calculate the future trajectory of a particle provided the current trajectory or the current position and velocity are known. Likewise, if you have a quantum particle, you use the Schrodinger equation to calculate the future properties provided you know where the particle is to begin with and what are the forces that act on the particle. Let me briefly request Professor Saxena, how much time do I have?
We just have about 35 minutes, another 5 minutes or so. Yeah.
Okay, so I'll try to close in 2-3 minutes so
Sure.
that there is
Sure.
room for
Yeah.
discussion.
Yes. Yes.
Yes. So here is an example which I have tried to show to illustrate the idea of tunneling to you. The wave functions are what are plotted here using a simple programming environment called Mathematica. And if the students are interested in pursuing modeling and simulations, I would strongly encourage you to learn programming and to pick up some of the programming skills which would enable you to infer a lot of properties as you go along. And this example tells you that for a simple model problem like this, you can calculate the wave functions, and the red regions of the wave functions clearly tell you that there is a non-zero probability for the particle to be found on the other side of the wall, despite the energy of the particle being lower than the barrier that the particle sees. Now, classically speaking, we are not really familiar with these ideas. I mean, how can I possess the low energy lower than the barrier, and how can I be able to yet cross the barrier? This seems like a paradox, right? And there are a lot of surprises of this kind in quantum mechanics. In fact, Niels Bohr said that if anybody is not surprised by quantum mechanics, they have not understood it. It is as simple as that, because it has a lot of surprises, because there is no way that we can relate our classical world to the quantum mechanical features that arise. Okay, and I'm sure you will get to get familiarized with excitements of quantum mechanics as you pursue bachelor's and master's degrees. But the idea of this talk is to tell you that modeling and simulation do have a large role to play in chemistry research. Chemistry is no longer an experimental science. Okay, and I have tried to illustrate to you a particular research problem of permeation through carbon membranes. And I have tried to tell you that using modeling and simulations, you can actually design smart membranes that can go on to become technologies when they enable separation of various chemical species. All right, so due to, again, time constraints, I shall close my talk with this. But before I do that, I would like to take a minute in thanking the people that have contributed to some of the research that I have talked to you about. I hope I have conveyed to you the excitements of a theoretical chemist in contributing to chemistry research. And if any of you are interested to know a bit more, you're welcome to write to me. Thank you very much for all your attention.
Thank you. Thank you very much, Dr. Swathi, for such an interesting talk. I am sure that the students, the school students, they may not be aware about all these things, and your talk must have enlightened them with all these new topics, which may not be very much there in their school textbooks, but it's always relevant to learn new things. Oh, so there are a few questions. So
Yeah.
shall I take up one by one?
Yeah.
Okay, fine. So the first one is, which technique we use for separating items at different boiling point?
Distillation.
Okay. Why graphene is not a compound used in daily routine, even though its high tensile strength, and are these used or can be used in RO water filtrations?
Yeah, so graphene is still not very popular in terms of becoming real technologies. People are attempting many applications, and some of them are already into the market. As I have said, it's extremely difficult to characterize single layer graphene. Okay, most often what we do is we use what is known as a scotch tape technique to peel layers from graphite, and most often we end up with few layers. It could be 5 layers, 6 layers, 7 layers, and so to really go down to single layer is extremely difficult. Okay, and that is why for graphene to go on to become technology, it is still highly non-trivial. But having said that, there are many solution-based processing technologies today which have been successful in actually leading to certain applications. Reverse osmosis membrane-based filtration is one. Not pristine graphene, meaning without any pores, but graphene membrane with pores has been adopted for such applications.
Okay, I'll take up the next one. Why is graphene being used as a single layer species for separation? Are there any other elements that form these layers?
So basically, there are a variety of membrane-based separation applications that are being pursued. One is single layer, which I have talked to you about. The other example is multi-layer graphenes. There are also other systems, which, for example, hexagonal boron nitride layers are very, very popular today. So hexagonal boron nitride layers, again, are very similar in architecture to the graphene layers. Okay, there are also reports very recently of transition metal dichalcogenide membranes, MOS2, MOSC2, and these are again layered materials which have been explored for some applications. But by far most popular seems to be graphene. And multi-layers, yes, they are being explored, not just single layer.
Okay, I'll take up the next one. Can graphene meshes be used to separate or filter harmful ions from water?
Yes, that's precisely what I tried to tell you, that graphene nanomeshes are employed, and one very specific form of carbon membranes, again, graphenes, is what I have illustrated on one of the slides.
Okay. Can't we use vacuum and cooling effects to separate mixture of gases and separate them?
That's right. So basically, low temperature methods are what one resorts to in some of these applications. If you look at the example of helium-3 from helium-4 that I have shown, you really need to go down to low temperatures, 20 to 40 Kelvin, for you to have a clear manifestation of the quantum features. Okay, what happens is we are exploiting the phenomena of tunneling here to separate helium-3 from helium-4. And that is significant only at very low temperatures. If you think of high temperatures, it's all classical phenomena that dominate. So the quantum effects actually die down, which means if you were to separate such species, there is no way but to go down to low temperatures. So that's an extremely important question that was raised.
Okay, I'll take up the next one. This is a quite basic one. What is the difference between diffusion and selectivity? And why do selectivities decrease with increase in temperature?
Okay, so when I say diffusion, it's basically the rates that I'm talking about. Okay, so the rate, I mean, I'm sure you're familiar with Arrhenius equation, right? The rate constant has an Arrhenius exponential temperature dependent feature. Okay, all of you are familiar with K equals A times exponential minus EA by RT. If you think of a chemical reaction, the rate is basically governed by two features. One, the temperature, two, the energy barrier for that particular process. That's what is denoted as the activation energy. Now, higher the temperature, higher will be the rate of the process. That's very obvious to see, because when you have high temperature, the particles jiggling and wiggling increases, and that increases the propensity of a chemical reaction, to put it in a very physical way. All right, but now when you think of selectivities, you are basically taking ratio of two rates, and the higher selectivity is achieved only when you go down to very low temperatures. At high temperature, what happens is this jiggling and wiggling is there for both particles, and therefore you cannot separate them. In some sense, it also has a mathematical answer, but I think it's better that we keep it to physical arguments at this stage.
Sure, sure. I'll take up the second last question now. Graphite is a good conductor of electricity despite being a non-metal. Does graphene conduct electricity and heat?
Yes, it does. In fact, graphene has very, very popular and interesting exotic property that has been heavily utilized. Graphene is what is known as a semi-metal. Okay, metals, as you know, are electrically conducting. If you think of, let's say, boron nitride, it's an insulator. Okay, there is a wide band gap. But for graphene, what happens is that the valence band and the conduction band touch at a very single point, which is known as the Dirac point. Okay, metals, we know they are good conductors, but then when you have a Dirac point coming in, it brings in a lot of exotic electronic properties, and a lot of excitement in graphene is because of that. Okay.
Okay. I'll take up the last question now. Can we use peptide sheets for such filtration?
Can we use
Peptide sheets.
peptide sheets? That's again a very interesting question. A few years back, there was a report again simulations which said that you can have cyclic peptide structures to achieve separation between species. Now, why do I say cyclic peptide structures? You know that when you think of peptides, these are the CONH bonds, right? You can design the peptide architecture such that they form a cyclic structure. Okay, and then you can, just like what we have done for graphene nanomeshes, you can look at selective separation. So this has indeed been reported. Thanks for bringing up this important
Sure.
question.
Let me just take one more scan at the chat section, because I've been copy pasting most of the questions. Let me just see if I think I've taken up all. Okay, well, there's one last. How are graphene batteries possible? I mean, something I think different question from the area, but still, I mean, if you would like to take up this one.
Yeah, sure, because it's in some sense related to my research also. We look at diffusion of lithium. As all of you know, lithium ion batteries are extremely popular today, heavily used, right? So at the heart of lithium ion batteries, what is important is the diffusion of lithium ions through the porous architectures. Okay, you need to have, from the electrode materials, facile diffusion, which is basically out of plane diffusion. Okay, so if you have a membrane like this, which has a planar architecture, you can think of in plane, which is this motion. You can think of out of plane, which is this motion. Okay, so using graphene as electrode material, there have been reports where you could use them for lithium ion battery applications as electrodes. That's precisely coming from the fact that they allow in plane and out of plane diffusion through the pores.
Okay, I think, yeah, so you have answered nearly all possible questions and within the stipulated time of 45 minutes. Thank you very much, Dr. Swathi. And now my request, Dr. Vinod Kumar, to give a vote of thanks on behalf of the college and the organizing team.
Thank you, Manoj.
Thank you very much, sir.
On the behalf of organizing committee, I thank Dr. Swathi for giving a nice lecture, and I think this lecture may ignite some young minds to pursue chemistry as their career. I think this topic was not for the students of 9th or 10th class, but I think the teacher who are attending this webinar, they must explain what she was trying to explain the things. And this is a new topic, and this is many people, they are pursuing their career in this type of the research, and this is a very nice topic, and the young minds may take this chemistry as a career in the future. I thank again Dr. Swathi for sparing her time and giving a nice lecture. Thank you. Thank you all attendees. Thank you
very much.
Thank you very much, Dr. Vinod. And I hope, Dr. Swathi, if possible, we may again contact you if you find some other interesting topic for students of class 11th, 12th, or 9th or 10th accordingly. And if in any way we can also have some practical, because some of the students, they have also asked that if we can have some practical demonstration also of the simulation work which you have shared or the practical work which is going on. It's like they are asking for like a virtual lab visit, if it is anyhow possible, of your laboratory. So then, they do not get a chance to see certain equipments and also the software tools. So any particular software you think that the students or teachers can access for their basic understanding for this particular topic?
I think it is difficult to.
It is difficult. Okay, no problem.
Because
sure.
most of those calculations are non-trivial, and for students it might be a little tricky.
Fine, no problem. So we'll be in touch, and they are asking for that. Can we upload this recording on YouTube? So I've already seek your permission, and after the webinar is over, I will be definitely uploading these recordings on the YouTube. Yeah.
One more thing, Manoj, I would like to tell Dr. Swathi that we have one thing common. I have done my 4-year integrated course, that is BSc Honors B.Ed from Regional Institute of Education, Ajmer, and she has done Mysore.
Very glad to know that. Very pleased.
So I hope that maybe
Then
Dr.
I went to
Swathi.
IIT Roorkee and you went to IIT Guwahati for pursuing your MSc.
Yes.
So maybe once the situation, pandemic situation is over, then if it is anyhow possible, we can arrange for a physical visit to our
Yeah.
institute. We'll be more than glad to host your talk again in person in Delhi itself.
Thank you.
Thank you very much.
Thank you
And
very
thank you
much.
very much all the panelists, Dr. Priya, Dr. Vinod, and all the attendees, the students and the teachers who have been there all throughout these last 45 minutes with us. Thank you very much.
Thank you. May I leave now?
Yeah, please. Sure.
Thank you.